Okay, so for the next part, I'm showing some videos off of YouTube for ROS and the potentials that it actually has as a method to try to get you guys to really like it. So we'll start using it early on. So here you see a colored object that's being detected, sort of just like what we showed before in the little setup. But basically you have image data coming in, the processed image is right here, and then you outline the original image and you publish that back out so you can view it. So that would be a normal process if you're trying to see something, see what it is that you're actually capturing with your camera and your image processing algorithm. As you can see though, there's some little points here and there that aren't necessarily what you want. So you're going to have noise, of course you're going to capture just the solid mass. And then you're going to have the overhead lighting effect on the ball itself. If you're trying to do any sort of color object detection, please come see me, because I have some methods you can use that I would like share if you want, which will get you something more like this. So Brad was raising his hand, please share it with me. Okay, so really, whatever you can do with OpenCV, you can also do with ROS. Because with OpenCV, the traditional way is maybe that you're just processing a video or some frames, and not necessarily what you would expect from like an active system. So with OpenCV, this could be like a video that you already recorded. It could be something that maybe they're bringing in through OpenCV's capture routines. But in the end, it's basically a single program doing one thing that doesn't talk with other programs unless you really make it, which is probably going to be more of a pain for you to do than just using ROS in the first place and OpenCV as something that you just use.
That's what I ROSified for our program.
Huh?
I ROSified that for our program.
Oh, this exact one?
Yes.
Yeah. So sometimes you find a lot of open source already completed algorithms that you may want to modify and improve and put on a robot. Or put on the cloud if you guys are interested in processing images and distributing them to many nodes, for example. Or just more of what I'm interested in.
And you can find more source in Visual Studio.
Yes. I was actually going to have a portion where I compared doing something in Visual Studio to doing something in ROS. I'll probably leave that till next class. But as you can see, this is actually a pretty decent method for you to see what you can do in OpenCV. But like the previous example, you can show the same thing in an OpenCV window inside of ROS and actually do something about these positions. Maybe you want to line up with the yellow object. At which point now the robot will be kind of going left and right because there's the yellow disturbance. So I can also show you some OpenCV, the actual website, so you can see where to get some of the different components. This, for example, is a car counting algorithm. Again, it's not a robot. It's just a camera on top of a pole. But you can use ROS to acquire these images and put them out to wherever you need to on your network, which could be very simple in the end for what you want to do. Especially if this is a camera that has, that's basically open to ROS. It would really help. So as you see here, it's just kind of cars and trucks and larger trucks. So you can do any number of different things. So if you look for OpenCV tutorials, there's a version 2 and a version 3. It kind of goes with which version of Python, I believe, that you have. Either version 2 or 3, usually I use 2. For the SLAM people, they're probably going to work a lot at this feature 2D.
2D, yeah.
Mostly in these types of programs and tutorials. So feature detection and then matching. There are some very particular matching algorithms that we like versus some other ones we can meet. Because also they get that information from our documents. So many different things you can actually do in OpenCV. You can extend a lot of these things into your robot, assuming that these applications, these tutorials don't take maybe 5 hours to complete. So if it's like 5 hours maybe on one picture or something insane like that, then it might not be applicable to a robot. You really have to test the algorithm first, maybe just in OpenCV, see if it's really going to work for what you want, then modify it to work with ROS, if you're doing anything with image data. And that may go for a lot of people. So you can also do different types of like machine learning and different things on images. So maybe something that you're thinking of just using like the sonar might be better suited with the camera as far as the sensor goes. So that's a whole other story for more robotic applications. But I'll go back to this output of the ROS graph. And I can show you a little bit of what's going on here. So every time you run a program, you're going to get some new boxes and new ovals and new links in between your different programs. At least you hope there's links. So here we have a number of different boxes going everywhere. So these are actually links going into the transform package. Transforms are like this. Well, I'm zoomed in and I'll show you the one example. This is ROS. It's a program that you would use to view things about your robot. So the transforms, in this case, are actually, you guys are actually learning about transforms, right? The serial manipulators? Okay. So this will look very familiar to you. Are you already doing DH parameters?
Yep.
Yeah. Okay. So on this, you would actually see, your X, Y, and Z. I believe, of course, the Z is probably going to be blue. What you have here is basically, you need to have a couple points identified in your model. You need to have a base point where everything actually goes down to. So from this base point, you would define all different relations. So in this case, it's that assistive robot, which is a Roomba on the under portion. So here's one of the wheels, here's another wheel. So reference to the center of mass, and the center of gravity axis. What you're going to have here is the base link. And that base link goes up to the different links that are relative, of course measured out relative to that one. And you're going to have some sort of angular changes here and there. So in this case, it's the camera that's looking down a little bit. I have it to where I can get IMU data and adjust the level of the camera, which is very important. When you look at the kind of data that I'm working with, if I zoom out a little bit, I can show you that. This diagram actually is the representation of how all the data is moving in these pictures. So what you see right here is some raw data from a camera just like this, but this one is actually the Microsoft Kinect camera. And what you're seeing are these objects that are on the floor. And you can see the shadows created behind the objects because this camera actually projects infrared light and then reads the infrared light with the infrared camera. So you see some shadows. Where there's shadows, you see these, you should be able to see it, these little green shapes. These green shapes, for instance, are this bottle, a tennis ball, and 2 wiffle balls. The virtual shapes, these spheres, are put where there are no obstacles in the way. So in this case, you're going to put this red, this is just my visualization method, but you're going to put these red spheres everywhere there's basically nothing green sticking out from the form. And there's another step I don't think I showed in this, but I flatten this data out as well using this angle. So then what you end up with is what should look like a nice flat surface with things on top of the surface, which then you can actually tell what is actually in your way. Because sometimes you don't actually get to see what's in your way. This container is kind of clear, but you still see basically kind of like the edge of it. Well, it's kind of translucent, so you're going to get some light going through it, but not too much. So in this case, you're going to see the edge of it. You may not see what's inside of it, but you will probably know that there's some problem. And here's the same image, but actually in the infrared image itself. That's why you see all this bright light, which you don't see in this image, which is the color image. And this has the depth overlay and also the process data overlay. Okay. So those components actually account for that's showing this, but the different tilts on the camera are accounted for by this portion right here, which is basically just the transform package requirements that you have all the different links. So you have the camera base link and some extra links on top of that. Those links all are necessary to define how the camera works in terms of all these different lenses and the cameras and the projector. So also going into this transform package is the robot state. So basically, what angle do I have the camera? Like 15 degrees down? So this robot state publisher needs to exist to publish into the transform package, which takes its joint states from the joint state publisher, which gets them from another topic, gets them from another topic, which are basically from the Connect IMU. So this is the ASUS version. The Microsoft Connect has an accelerometer, which at most you can use for determining the pose of the camera. So the data comes in through here. The what was this one? The current tilt angle that I calculate kind of based off this IMU data is also going into the joint state node. And all this data is coming out of the tilt angle, which is coming from the Connect's particular node that you have to run to actually get the tilt angle and also set the LEDs on the Connect. So this is one program that provides you this data. There's another one or two programs that well, these are actually static transforms that you set initially. And then this other portion is what helps you actually drive the robot. So here we have a serial node, which the serial refers to the connection with your Arduino. So in essence, whenever I set one of these topics with some data, it happened to be for the arm that would extend and reach to a particular position. These are all the different servos that I would set. Then also, if I wanted to change the tilt angle to connect, I would send a command on that particular topic. And then here you have that command mill, which I showed you before, which is a twist message. So the robot takes the twist message and it goes to the serial lines to the Arduino, and then the Arduino does the rest. And the Arduino can actually run ROS as well. So once you start working with it, you're kind of thinking, maybe I don't want to write all these serial commands to ferry data back and forth between the Arduino and my computer. maybe I want something to do that for me. And once you figure you can do that, and hopefully do it with a lot of care, because you can actually really mess things up. If you try to publish to your Arduino faster than you can actually like do that, then it will actually be a really nice addition into your system. Because a lot of you are probably doing some new design projects that have to have a computer interfacing with, say, like an Arduino or some sort of microcontroller. That might be something to help you. I've already talked to a few people in here about doing just that. So this is what's happening in the prior diagram. There's a lot of extra stuff behind the scenes that's not even added to these pictures. These little tags right here, they're kind of important for people that want to use this this project. I'm showing you a video might just be the better way to show you. And then I'll show the augmented reality version of it. Let's try to find one with that. Okay, so these little tags can be detected with just about any camera, as long as you have some special nodes set up to allow for calibration of your camera. So you can detect the nodes in different positions, and the best part about it tells you in 3D space how they actually look. So if you're needing to actually detect something in a certain pose, you can use these tags. So this particular robot is a PR2 made by Willow Garage, which is basically the same group that made ROS. At least the group that started ROS, and everybody else kind of contributed, made it better, and really enhanced it in many different ways. This is actually a good example of a group that made ROS better with these tags. There's many different groups that use OpenCV to do different things. This is just one of them. So you can even make bundles of tags that represent something that you want to maybe grasp with more accuracy. But sometimes there's a little bit of error in detecting these tags in the right places. So we've used these before, actually to do something like this, to where this wasn't actually a humanoid robot. This is a Pioneer 2 robot, which is the red robot in the base lab, with a camera on it. And we would detect these targets and direct the robot to move how we want it to. So we have a video somewhere of Mohan Kumar, who's now working with the Open Cloud Institute, holding a panel. And I think also Bharat was doing the same thing. Holding a panel, and the robot was kind of chasing it. Of course, if we got too close, you can make it move away by pushing the panel closer to the robot. But we did this all over the cloud using ROS. And it was actually pretty good. I think it was actually really good. Seeing that we set up the system over in the ACE lab, and we brought it all the way to the HEB University Center and ran the demo there without any problem. Maybe we had to make sure everything was still plugged in. I think we had like some loose cables over there. But really everything just worked. So we were sending data from the camera. In this case, this little guy's got a camera.
Yeah.
Sorry about not using the presentation version. These things are kind of hard to see. So right here he's got a camera, which you can see the target. So these images that he's capturing get sent over the cloud. And at the time we're using the UTSA Research Data Center Cloud. It's over in the MS building. It's big for what the school has here on campus. We would process the images over in the cloud with the AR track all of this package right here. It's kind of fun to set up, quite a few steps initially, but once you set it up, you'll be happy because you can detect whatever it is that's going on with the images quite nicely. So we process it here in the cloud, send it back over the router. The whole, basically the whole difficulty And doing this whole setup was actually just the processing. Like just actually getting that package to work was the hardest part. Because ROS basically allows that type of setup to exist in your system pretty easily. You can really easily repeat this experiment. Which if anybody's doing anything for maybe the cloud class or maybe for the robotics class where they want to use the cloud in some way, this was actually a very nice experiment showing you how it can work. So, as I said, the image is transmitted across, control vectors come back, and the robot moves to its target based on how you want it to. So here we could actually put a very complicated algorithm. Maybe, say for the SLAM group, that's probably where we're going to be doing most of the processing. Because as young guy mentioned, he's wondering about like which computer he's going to use. So I'd rather put everything in our cloud on the was it the West Campus?
Field
Yeah, the
lab.
West Campus, Field Lab. So over there we have 10 servers, 9 of which are actually used for computation. Once I get it working again, which seems to be every time the power goes out, I gotta redo it, which is the major problem right now with having your own little cloud, is managing it yourself. So I gotta set it up again. It'll probably just take a day. If anybody wants to see that, you can come watch, come help, whatever you want to do. But once we have it going, we can actually use that as our place to process images for the robots, which is actually pretty good because I was having some trouble getting a particular package of OpenCV to work for SLAM in detecting the different features. So actually on the little boards like this one. So it'd be a very good thing to do. So how are we going to use ROS, right? There's a whole bunch of different commands you can use. I can show you a cheat sheet of them. The most basic ones you're going to be using a lot are ROS run. So a typical command looks kind of funny, looks kind of redundant. ROS run, image view, seems kind of redundant, right? Image, := camera, RGB, image raw. If I have the memory card in this guy, I'd be able to show you how that works. But basically that's what you need to do to see the image coming out of this guy. Assuming you've already started the node that pulls the camera for its images and puts them out on the network. So ROS port is a program that basically sets up the master in your network. So the ROS network will include a master and then a whole bunch of nodes, as you saw before on that diagram right here. Somewhere here there's a ROS port. It's probably not shown because I have more parts to this diagram. Yeah, and then include the rest of the parts. There's actually like 4 more panels of information going on here to make all this work. So a ROS port just sets up the master so that the rest of the nodes can actually start. So this would be one of the nodes that you'd be starting. This is from the package image view. And they got very creative with the name of the program that you're running from the package. It's the same name as the package. It's kind of, like I said, redundant, but that's what happens. So here's where you have my funny package name, and then my program name. Which we'll get more into that next time with the working computer. So ROS launch is a combination of these two. And a little bit more. So ROS launch starts a ROS master if one does not exist. And it will run a program with a launch file. The launch file actually describes which programs will run. This OpenEye launch is actually the package name. So this launch file has the names of all the programs you're going to run, the different parameters, and which order basically to run them in. And whether or not you want to fail completely, say, if one of those nodes does not start. So if your camera doesn't exist, do you start the robot on a camera, like image processing algorithm? The answer probably no. You don't start an image processing if the camera's not plugged in. So that's where you probably make it fail within this one file. Just quit everything and basically show the user there's something wrong. When you're building your code in ROS operating system, I can show you that next time. I'll show you some examples in the tutorials. A ROS CD will get you to the directory for which your code is in. Basically, if you want to do ROS CD open and launch, you can automatically change directory into that open and launch directory, wherever that is. That's kind of the beauty of it. You don't have to know where it is. I could tell you it's in the folder opt-ROS, Indigo, share, open and I launch, and then you can go from there. Are you going to remember all that? I just told you that a few different directory names. You're not going to remember it. So ROS CD may actually help you. ROS Pack profile. Once you add a new package to your system, you want to run ROS Pack profile. The reason being is that a new package is probably not necessarily picked up by the ROS indexer, which will allow you to do ROS CD. So it's not in the index, you can't just automatically change directory into it. So it's not as direct. So there's also a program called CAD-CAM-Make that you will definitely have to use if you're going to be building new code. And when I mean building new code, you're going to be doing that with C++. Even with Python, you do have to run CAD-CAM-Make when you have your own messages defined. So here's a typical program you're going to be writing in tutorials. And don't get too scared of it. This is C++. Yeah, people don't like C++. How many people like C++? How many like Python? You guys like slow code? You guys like slow code. Okay, so I say Python is slow code because it's interpreted. It is not compiled. So the kind of benefits you're going to get from compiled code is like night and day, but still Python is like night and day to MATLAB. So people that use MATLAB for heavy operations, you're going to notice that it's very, very slow. And Python is usually faster than that. And then C++ is probably like 10 times faster than MATLAB ever could be, even though some programs you can make in MATLAB use C++. So this may be an uglier example to look at, but for those that actually like C++, you can read it. Those who don't, you need to learn it if you want to use C++. But it's all up to you, because here's the C++ version. There's also a Python one. Those people who love Python. And they removed most of the comments to make it look like the Python one's very simple. And really, the code is almost the same length. There's maybe 5 or 10 more obligatory lines in C++. But overall, they work basically the same. There are some features you don't get in Python that you get in C++. But that's more or less when you're looking for performance. But I can tell you all about that if you want to hear it. But for example, this is actually a publisher and subscriber. So you would make the publisher node in this example. So here's where you would basically advertise the fact that you're going to be publishing something called chatter, which is a string. So you're just going to send a string out from this program. And then you have to initialize your node. You have to set a rate for which you're going to be doing this while loop, because this loop is just going to say, hello world, hello world, hello world, hello world, forever. which is not very useful, but that's what it does. It's an example and shows you how to do things. So it'll tell you hello world at a rate of 10 hertz. And you can go more into this example, but overall it's a very, very simple example. And it's about half of what you would do for a controller. Controllers do what? Oh, control stuff, okay. But hopefully with control, it would be this, right? So this is actually a number and you're telling your motor or whatever to do whatever. This would be open to control. So you can actually make a node that does both, subscribe and publish. That would be more or less a closed loop if you actually close the loop. Just because you have a subscriber and publisher, you can't just say, hey, I got a closed loop system. Not the case. But we're going to cut it right here for